Welcome to our journey through the cosmos, where we explore the greatest science mysteries in the universe. Before us lies a vast cosmic ocean, teeming with more stars than grains of sand on all the beaches on Earth. And yet, for all our advances in science and technology, we've only just begun to dip our toes into this vast ocean of knowledge. From the enigmatic dark matter to the perplexing nature of time, join us as we delve into the unknown. We'll journey to the edge of black holes, unravel the secrets of quantum entanglement, and explore the possibility of other universes. Our quest is to understand our place in the cosmos, to grasp the fundamental laws governing the universe, and to push the boundaries of human knowledge. Get ready to expand your mind and ignite your curiosity as we embark on this grand adventure together. The universe awaits, filled with mysteries waiting to be unraveled. Our cosmic journey begins with a perplexing mystery that has baffled astronomers for decades: dark matter. Imagine this: galaxies, vast islands of stars swirling in the cosmos, held together by a force we can't see or touch. That force, my friends, is gravity, the invisible hand that sculpts the universe. But here's the catch: there's not enough visible matter, the stars and gas we can see, to account for the gravitational pull that binds these galaxies together. Enter dark matter, the elusive substance that makes up the vast majority of the universe's mass. We can't see it directly, but we know it's there because of its gravitational effects. Scientists are currently on the hunt for dark matter particles using powerful instruments like the Large Hadron Collider, smashing atoms together at incredible speeds, hoping to catch a glimpse of these elusive particles. The discovery of dark matter would revolutionize our understanding of the universe, revealing the building blocks of our cosmos. Now, let's venture into the bizarre world of quantum mechanics, where particles behave in ways that defy common sense. Imagine two particles separated by vast distances, billions of light years even, yet mysteriously linked. This is quantum entanglement, a phenomenon that Einstein himself famously called spooky action at a distance. When you measure the state of one entangled particle, the state of the other particle instantly collapses into the opposite state, no matter how far apart they are. It's as if these particles are communicating faster than the speed of light, violating our classical understanding of physics. But here's the even more mind-boggling part. Quantum entanglement has the potential to revolutionize computing, leading to ultra-powerful quantum computers capable of solving problems that would take classical computers billions of years. Experiments are underway to harness the power of entanglement, paving the way for a new era of quantum technology. Our galaxy, the Milky Way, is a vast cosmic city teeming with hundreds of billions of stars. Given the sheer number of stars and planets in our galaxy alone, it seems statistically improbable that we are alone in the universe. So where is everyone? This, my friends, is the heart of the Fermi Paradox. The paradox highlights the discrepancy between the high probability of extraterrestrial life and the lack of contact with such civilizations. One possible explanation is the Great Filter, a hypothetical barrier that prevents life from reaching advanced stages or makes it incredibly difficult for civilizations to communicate across interstellar distances. The search for extraterrestrial intelligence, or SETI, is actively searching for signs of alien civilizations, scanning the cosmos for radio signals or other techno-signatures. The discovery of even a faint signal from an alien civilization would have profound implications for humanity, confirming that we are not alone in the universe. Imagine a gravitational giant, a cosmic monster lurking in the depths of space, pulling entire galaxies towards it with irresistible force. This, my friends, is the Great Attractor, a gravitational anomaly that has puzzled astronomers for decades. Located millions of light years away, the Great Attractor is a region of space towards which our galaxy and millions of other galaxies are being drawn. Its gravitational pull is so strong that it's affecting the motion of galaxies over a vast region of the universe. Scientists are working tirelessly to map the Great Attractor and understand its nature. The challenge lies in the fact that it's obscured by our own galaxy's dust and gas, making it difficult to observe directly. Unraveling the mystery of the Great Attractor could provide crucial insights into the large-scale structure of the universe. Now, let's delve into one of the most profound discoveries in modern cosmology, the accelerating expansion of the universe. Imagine the universe as a balloon being inflated. You might expect the expansion to slow down over time due to gravity, but observations have shown the opposite. The expansion is speeding up. This mind-boggling discovery led scientists to propose the existence of dark energy, a mysterious force that makes up the vast majority of the universe's energy density and counteracts gravity, driving the accelerated expansion. We know very little about dark energy, but its existence has profound implications for the fate of the universe. Projects like the Dark Energy Survey are mapping the distribution of galaxies and studying distant supernovae to measure the properties of dark energy and understand its role in the universe's evolution. The quest to understand dark energy is a quest to understand the very fabric of space-time. Time, my friends, is one of the most fundamental concepts in physics, yet it remains one of the most elusive. We experience time as a linear progression from the past to the present and into the future. But what exactly is time? Is it an illusion, as some physicists suggest, or a fundamental property of the universe? Some theories propose that time is an emergent property, arising from a deeper, more fundamental reality. Others suggest that time may be granular, quantized into tiny, indivisible units, much like energy is quantized into photons. Researchers in quantum mechanics are exploring the nature of time by studying how particles behave at the quantum level. Experiments are underway to see if time can be manipulated or even reversed, potentially opening up mind-boggling possibilities for time travel. In the heart of the standard model of particle physics lies a fundamental particle that gives mass to all other particles, the Higgs boson. Imagine a cosmic molasses, a field that permeates all of space. Particles acquire mass by interacting with this field. Much like objects moving through molasses experience resistance. The Higgs boson is the quantum excitation of this field, the particle that gives the field its properties. Its discovery in 2012 at the Large Hadron Collider was a triumph of modern physics, confirming the existence of the Higgs field and completing the standard model. The discovery of the Higgs boson has profound implications for our understanding of the universe. It explains why particles have mass, which is crucial for the formation of stars, planets, and even life itself. Gravity, the force that holds us to the Earth and governs the motion of celestial objects, is described by Einstein's theory of general relativity. General relativity has been incredibly successful in explaining the behavior of gravity on large scales, from the bending of starlight around massive objects to the expansion of the universe. However, general relativity breaks down at the quantum level, the realm of atoms and subatomic particles. This has led physicists on a quest to develop a quantum theory of gravity, a theory that can unify gravity with the other fundamental forces of nature. String theory is one such candidate for a quantum theory of gravity, proposing that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. Understanding the true nature of gravity is crucial for unraveling the mysteries of black holes, the Big Bang, and the very fabric of space-time. The vastness of the universe, combined with the sheer number of stars and planets, suggests that life beyond Earth is not just possible, but probable. And yet, we haven't found any concrete evidence of extraterrestrial civilizations. This is the great silence, the perplexing absence of alien signals. One possible explanation is that life is incredibly rare and intelligent life even more so. The conditions for life to arise and evolve into intelligent beings may be so specific that Earth is the only planet in the observable universe where it has occurred. Another possibility is that advanced civilizations exist but choose not to communicate or are unable to do so due to technological limitations or the vast distances involved. The search for extraterrestrial intelligence continues, with scientists constantly developing new ways to listen for alien signals and explore the cosmos for signs of life. At the heart of modern physics lies a fundamental challenge, unifying the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single, elegant framework. Quantum gravity is the holy grail of this quest, a theory that can describe gravity at the quantum level and reconcile it with the other three forces. One of the main obstacles to unifying gravity with quantum mechanics is the vastly different scales at which they operate. Gravity is incredibly weak compared to the other forces, making it extremely difficult to study at the quantum level. Despite these challenges, physicists are making progress towards a theory of quantum gravity. String theory, loop quantum gravity, and other theoretical frameworks offer promising avenues for unifying the forces of nature and understanding the universe at its most fundamental level. Black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape, are among the most fascinating and mysterious objects in the universe. Imagine a region of space where the fabric of space-time is infinitely curved, leading to a point of infinite density known as a singularity. Black holes form when massive stars collapse at the end of their lives, their cores collapsing under their own gravity until they reach a point of infinite density. These cosmic abysses warp space-time around them, creating gravitational wells from which nothing can escape. Astronomers have observed black holes indirectly by studying their effects on surrounding matter. For example, as matter falls into a black hole, it forms an accretion disk of hot gas that emits X-rays, which can be detected by telescopes. The study of black holes provides insights into the extreme limits of gravity and the nature of space-time. Our universe, vast and awe-inspiring as it is, may be just one of many universes in a grander multiverse. Imagine a cosmic tapestry woven with countless threads, each thread representing a different universe with its own unique set of physical laws and constants. The idea of a multiverse arises from various theoretical frameworks, including cosmic inflation, string theory, and quantum mechanics. For example, cosmic inflation, a period of rapid expansion in the early universe, could have created bubbles of space-time that evolved into separate universes. While the multiverse remains a highly speculative idea, it has captured the imaginations of physicists and cosmologists alike. The possibility of other universes, each with its own unique properties and histories, raises profound questions about the nature of reality and our place in the cosmos. Time travel, the tantalizing possibility of journeying through time, has captured the imaginations of scientists and science fiction writers alike. While time travel may seem like the stuff of fantasy, Einstein's theory of general relativity suggests that it might be possible, at least in theory. General relativity describes gravity as the curvature of space-time, and according to the theory, it's possible to warp space-time to such an extent that time loops back on itself, creating closed time-like curves, or wormholes. These wormholes could potentially act as shortcuts through space-time, allowing travelers to journey through time. However, even if time travel is theoretically possible, the technological challenges involved in creating wormholes or other means of time travel are immense and may well be insurmountable. Nevertheless, the possibility of time travel continues to intrigue and inspire physicists and dreamers alike. What is reality? It's a question that has perplexed philosophers and physicists for centuries. Our everyday experience suggests that reality is objective, independent of our minds, but quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels, challenges this view. Quantum mechanics suggests that reality is fundamentally uncertain and probabilistic. Particles do not have definite properties until they are measured, and the act of measurement itself influences the outcome. This has led some physicists to propose that consciousness plays a fundamental role in shaping reality. The nature of reality remains one of the most profound and debated topics in science and philosophy. Imagine looking back in time to the very beginning of the universe, to the moment of the Big Bang. While we can't travel back in time, we can observe the faint afterglow of the Big Bang, a cosmic echo that permeates all of space, the cosmic microwave background radiation. The cosmic microwave background, or CMB, is a faint glow of microwave radiation that fills the universe. It was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral atoms, allowing light to travel freely through space. By studying the CMB, cosmologists can learn about the early universe, its composition, and its evolution. Missions like the Planck satellite have mapped the CMB in exquisite detail, providing valuable insights into the Big Bang, inflation, and the fundamental parameters of our universe. Quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels, is full of surprises, including the bizarre phenomenon of quantum fluctuations. Imagine a vacuum, a region of space completely devoid of matter and energy. According to classical physics, nothing should happen in a vacuum. However, quantum mechanics tells us that even a vacuum is not truly empty. Instead, it's a seething sea of virtual particles, constantly popping in and out of existence. These virtual particles, known as quantum fluctuations, can have real effects on the universe. For example, quantum fluctuations are thought to have played a crucial role in the very early universe during a period of rapid expansion known as inflation. These fluctuations may have seeded the tiny density variations that eventually grew into the large-scale structures we observe in the universe today, such as galaxies and galaxy clusters. Light, the very essence that allows us to perceive the world around us, has puzzled scientists for centuries. Is light a wave, like ripples on a pond, or is it a particle, like tiny packets of energy? The answer, it turns out, is both. Light exhibits both wave-like and particle-like behavior, a concept known as wave-particle duality. Experiments like the double-slit experiment have demonstrated this duality, showing that light can interfere with itself like a wave while also exhibiting particle-like properties. This dual nature of light is a fundamental aspect of quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels. Understanding the nature of light is crucial for understanding the universe, from the smallest atoms to the largest galaxies. For every particle of matter, there exists an antiparticle with the same mass but opposite charge. For example, the antiparticle of the electron is the positron. When a particle and its antiparticle meet, they annihilate each other, releasing a burst of energy. According to the laws of physics, matter and antimatter should have been created in equal amounts during the Big Bang. However, our universe is dominated by matter, with very little antimatter to be found. This asymmetry, known as the matter-antimatter asymmetry, is one of the biggest unsolved mysteries in physics. Scientists at CERN and other laboratories around the world are searching for clues to explain this asymmetry. One possibility is that there is a subtle difference in the behavior of matter and antimatter, a difference that allowed a tiny excess of matter to survive the early universe, eventually forming the stars, planets, and galaxies we observe today. Imagine a world where electricity flows without any loss of energy, where power lines and electronic devices operate with perfect efficiency. This is the promise of superconductivity, a phenomenon in which certain materials exhibit zero electrical resistance at extremely low temperatures. Superconductivity arises from the strange world of quantum mechanics, where electrons, the carriers of electricity, can pair up and flow through the material without colliding with atoms, resulting in zero resistance. Superconducting materials have the potential to revolutionize many technologies, from power transmission to medical imaging. Scientists are constantly searching for new materials that exhibit superconductivity at higher temperatures, making them more practical for everyday applications. The discovery of room temperature superconductivity would be a groundbreaking achievement, ushering in a new era of technological advancement. Time, as we perceive it in our everyday lives, seems constant and unchanging. However, Einstein's theory of special relativity tells us that time is not absolute but relative to the observer's frame of reference. This means that time can pass at different rates for observers who are moving relative to each other or experiencing different gravitational fields. One of the most mind-boggling consequences of special relativity is time dilation, the phenomenon where time slows down for objects that are moving at speeds close to the speed of light or experiencing strong gravitational fields. Time dilation has been experimentally confirmed using atomic clocks flown on airplanes and satellites, demonstrating that time is not as constant as we might think. Time dilation has profound implications for our understanding of the universe and for technologies like GPS, which rely on precise timekeeping. Einstein's theory of general relativity predicts that massive objects, such as black holes and neutron stars, create ripples in the fabric of space-time as they move, similar to how a boat creates ripples in water. These ripples, known as gravitational waves, travel at the speed of light, carrying information about the objects that created them. Gravitational waves are incredibly faint and difficult to detect, but in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by directly detecting gravitational waves for the first time. The waves were produced by the merger of two black holes billions of light years away, confirming Einstein's theory and opening a new window into the universe. Gravitational wave astronomy is a rapidly growing field with new observatories being built around the world. By studying gravitational waves, astronomers can learn about some of the most violent events in the universe, such as black hole mergers and supernova explosions, providing insights into the nature of gravity and the evolution of the cosmos. The electron, a tiny, negatively charged particle that orbits the nucleus of an atom, is one of the fundamental building blocks of matter. Its mass, though incredibly small, is a fundamental constant in physics, playing a crucial role in determining the properties of atoms, molecules, and all matter in the universe. The electron's mass is so small that it's difficult to measure directly. However, physicists have developed incredibly precise techniques to determine its value, using methods such as penning traps, which use electric and magnetic fields to confine electrons and measure their properties. The precise value of the electron's mass is crucial for many areas of physics, including the Standard Model of particle physics, which describes the fundamental forces of nature and the particles that make up the universe. Understanding the electron's mass is essential for understanding the nature of matter and the universe itself. Time, as we experience it, flows inexorably forward, from the past to the present and into the future. We remember the past, but not the future, and we can influence the future, but not the past. This unidirectional flow of time is known as the arrow of time. The arrow of time is a fundamental aspect of our universe, but its origin remains a mystery. One possible explanation lies in the concept of entropy, a measure of disorder or randomness. The second law of thermodynamics states that entropy always increases over time in a closed system, and this increase in entropy could be responsible for the arrow of time. However, the relationship between entropy and the arrow of time is still not fully understood. Some physicists believe that the arrow of time may be related to quantum mechanics or cosmology, and research continues to explore this fundamental aspect of our universe. Contrary to popular belief, sound can exist in space, but it doesn't travel in the same way it does on Earth. Sound waves are vibrations that travel through a medium such as air or water. In the vacuum of space, there is no medium for sound waves to travel through, so we cannot hear sounds in the traditional sense. However, space is not a perfect vacuum. It contains trace amounts of gas and plasma, and these particles can carry sound waves, but these waves are extremely faint and require specialized instruments to detect. Furthermore, sound in space often takes the form of electromagnetic waves, such as radio waves, which can travel through the vacuum of space. By studying these electromagnetic waves, astronomers can learn about the movement of gas and plasma in space, providing insights into the dynamics of stars, galaxies, and other celestial objects. Cosmic rays are high-energy particles that bombard Earth from space, originating from sources both within and outside our galaxy. These particles, mostly protons and atomic nuclei, travel at nearly the speed of light, carrying vast amounts of energy. The origin of cosmic rays is still a mystery, but scientists believe they are produced by powerful cosmic events, such as supernova explosions, active galactic nuclei, and gamma-ray bursts. These events accelerate particles to incredibly high energies, sending them hurtling through space. When cosmic rays collide with Earth's atmosphere, they create showers of secondary particles that can be detected by ground-based observatories, such as the Pierre Auger Observatory. By studying cosmic rays, scientists can learn about the most energetic events in the universe and the properties of particles at extreme energies. Thank you for joining us on this cosmic journey. We've explored some of the greatest science mysteries in the universe, from the enigmatic dark matter to the perplexing nature of time. But our journey is far from over. The universe is vast and full of wonders, with countless mysteries yet to be unraveled. As we continue to explore the cosmos, we'll undoubtedly encounter new puzzles and challenges that will push the boundaries of our understanding. Stay curious and keep exploring the mysteries of the universe. Don't forget to like, share, and subscribe for more fascinating insights into the world of science. Until next time, keep looking up at the stars and wondering what mysteries they hold.